Hello everyone, welcome back to Knock Knock Air Education, and I hope all of you are doing good. So today we are going to study a topic, matrix representation of a linear transformation, and I'll try to cover this topic completely in this video itself, and if required we will do few practice questions in another video. So let's get started with the topic. So we have to study about the matrix representation of a linear transformation. So initially we will try to understand what is the matrix representation of a linear transformation and then how to find it out. So as the name itself suggests, that matrix representation is a matrix which represent a linear transformation. So we are today going to work upon the linear operator. A linear operator is nothing but a linear transformation from a vector space V to the vector space V itself. So what we have to do is that we have to find out a matrix which represents this linear transformation. So suppose I am saying that this matrix is A. But what we have to understand over here is that we always find the matrix representation of a linear transformation with respect to a standard basis or any ordered basis, right? So I mean to say that we should have a ordered basis, and with respect to that ordered basis we will find out a matrix which is going to represent this linear transformation. So this topic is very important. Why? Because all the properties that this matrix will be having are going to be the properties that this linear transformation has. Suppose somebody asks you to find out the determinant of the linear transformation T, the trace, the eigenvalues, rank, whatever you are being asked to find out about this linear transformation T, you can very easily find out the determinant, trace, eigenvalues, rank for this matrix A, and whatever values the matrix A will possess, they are going to be the values T is going to have. This is the benefit of this topic, that if somebody asks you about the properties of T, you can answer it with respect to the properties of A. Both are having the same properties, because students many times face problem while finding out the trace of this linear transformation, determinant, though we can find it out, but the very easiest way to find it out is that we just find a matrix that represent this linear transformation, and then we can work upon that matrix because we are very comfortable with that. That is the application part of this topic. Now initially in this lecture we will understand how to find out the matrix representation of a linear transformation, and then later on we will do a few questions so that we can develop a good understanding about this topic. So as I said that we need to have a basis. So suppose I am saying that the dimension of our given vector space V is n. So it implies that the any ordered basis of this vector space V will contain n number of vectors. So suppose I am saying that this v1, v2 up to vn are the vectors inside the basis B. So B is an ordered basis for this vector space V. So what we have to do for finding out the matrix representation is that by using the definition of this LT, we will find out Tv1, then we will find out Tv2, and in a similar way we will find out Tvn. And as you know that if B is the basis for this vector space V, then this B is going to be the set of linearly independent vectors, and a span of B is equals to V. And what does this statement imply? That for all vector V in the vector space V, there exists what? Ci from the field F for I equals to 1, 2, 3 up to n, such that this V will be the linear combination of the members of this basis B or Vi vectors, I running from 1 to n. So this V will be C1 V1 plus C2 V2 up to Cn Vn. So this is the property of the basis. So we are going to use this property only. So Tv1 is a member of where? This vector space V only. So any member of the vector space V can be represented as what? Can be represented as the linear combination of the basis members. In fact, we have studied that unique linear combination. So what I can do is that I can write it down A11 V1, A12 V2, and this is A1n Vn. In a similar way, here we have A21 V1 plus we have A22 V2, and in this way we will reach up to A2n Vn. So this last T of Vn can also be expressed as An1 V1 plus we have An2 V2, and in a similar way we will go up to Ann Vn. So now you can see one thing from these n number of equations, that I can write it down very easily. This is our TV1, then we have TV2, and then we have TVn, and here we have a matrix which is A11, A12 up to A1n, then we have A21, A22, then A2n, and here we have An1, An2, and then we have Ann, and here we have the column vector V1, V2, Vn. So from this last slide you can see very easily we can write it down. Even we have learned this process in the system of linear equations as well. So here this matrix is called as the coefficient matrix. So here is the solution that we get how to find the matrix representation of a linear transformation. So if we take the transpose of this matrix, then we will get the answer of our question what we were searching for, that the matrix representation of the linear transformation T with respect to the ordered basis B is the matrix A, and that is nothing but the transpose of this matrix that we obtained. This is our A21, A22, this is A2n, and then we got An1, An2, and then this is Ann, and we take the transpose of this matrix. So what matrix we got here is that this is going to be A11, A12, and then we have A1n because we have to take the transpose, A21, A22, then we have A2n, then we have An1, An2, and we have Ann. This is the matrix that we are getting. So the process is very simple. You will be given a standard ordered basis or any ordered basis and a defined linear transformation. So what you need to do is that you just need to find out the image of every basis member, and you need to write it down in the unique linear combination of the basis member itself. Now form the coefficient matrix, take the transpose of that, and you will get a matrix representation of a linear transformation with respect to any ordered basis. But here I will tell you a very important thing which all of you always miss, and even if you are reading it for the first time you cannot get anything about it. So this can be asked either in section A as a option, or in any interview the examiner may ask you that what does the columns of the matrix representation of a linear transformation represent. So this is the point where nobody focuses or nobody notices, but at least you should be concerned that if somebody asks you that if you are being given a linear transformation, an ordered basis, and you find out the matrix representation, then what are the columns representing? This is the point that you should notice here. So I will tell you. So before that I will tell you a very short concept that will give you a brief idea about it. All of you might have heard about coordinate vector. What is the coordinate vector? So suppose dimension of a vector space V is n, where V is a vector space. So the basis of the, any ordered basis of the vector space V will have n number of vectors. So we know that since the basis B can generate the whole vector space V, that is span of B will always be equal to V, it implies for all the vectors V inside the vector space V, there exist C1, C2 up to Cn, and these are unique scalars from the field F such that your V vector can be written as C1 V1 plus C2 V2 up to what? Up to Cn Vn. So if somebody asks you about the coordinate vector of V with respect to basis B, then that is going to be these scalars as a column vector. This is going to be the coordinate vector. Let me write down over here. This is the coordinate vector of V with respect to basis B. Now one important thing that I will mention here is that why I am always saying that ordered basis. Even in classes I have asked a student that make sure you always understand this word ordered basis. Why? Because let me give you one example. Suppose we have a vector space R2 over R, field is real number, okay, and I am taking one basis here as 1001, what we call as our standard basis, and suppose I am giving you a vector 2 comma 3. Okay, so if I ask you to write it down in the linear combination of the basis members, you will write it down like this, right? So if I ask you about the coordinate vector of this V with respect to basis B, what you are going to tell me? This is going to be 2 3. In case one of the student wrote it like this, which is completely okay, I am not saying there is any problem because the result is going to be the same, but the problem here is going to be this: if you are going to find out the coordinate vector, you will give your answer 3 2, and this will make a huge difference. Because why I am saying again and again the word ordered basis is because you cannot change the position of the vectors inside any basis. Why? Because once you changed the position of the vectors inside the basis, your coordinate vector will change and whole theory is going to change. So this coordinate vector is going to be with respect to another basis. If I consider B1 as 0 1 and 1 0, so now you know that this 2 comma 3 will be written as what? 3 times 0 1, then 2 times 1 comma 0, and now the coordinate vector with respect to B1 is going to be 3 2. Because according to you the things are same, either you write this or you write this, the expression is going to be same, but it will give a huge difference in coordinate vector. That's what I am telling you. Never change the position of the basis vectors anywhere. If you are writing it, write it in the same order. So I hope now the concept of coordinate vector is clear to all of you. This is the answer of the question that I was asking you few minutes back. That suppose in any interview somebody asks you while finding out the matrix representation of linear transformation, what does the first column represent, what does the second column represent. So here is the answer. So just let me erase this part because all of you have understood it. See the first TV1. If I ask you what is the coordinate vector of TV1 with respect to basis B. So obviously once you have written the linear combination, once you have written the linear combination, you will put all these scalars, because you know that if B is the basis, this linear combination is unique. There does not exist any other A11, A12, A1n which TV1 can be expressed like this. So this is the coordinate vector. I hope all of you got an idea about the coordinate vector. In a similar way, if I ask you about the coordinate vector of TV2 with respect to basis B, so you will write it down TV2 as the linear combination of the basis member. So what it is going to be? A21, A22 and A2n. In a similar way, if I ask you about the TVN, coordinate vector of TVN with respect to basis B, what it is going to be? It is going to be AN1, AN2 and this is ANN. So how simple is this? So here is the answer of your question. See, this is A11, A12, A1n, and what here it is? A11, A12, A1n. The next column that we have is A21, this is A21, this should be A22 and A2n, right? This is AN1, AN2 and ANN. So what we are getting here is that in this matrix, the first column is nothing but the coordinate vector of TV1 with respect to basis B. The second column is TV2 with respect to the basis B. So I hope now I have made that point clear to all of you which I was asking you. So this is TVN coordinate vector with respect to B and this is the matrix. So this C1 column, this C2 column and this is Cn. So C1 is actually representing the coordinate vector of TV1 with respect to B. C2 is actually representing TV2 coordinate vector with respect to B. Cn is actually representing TVN coordinate vector with respect to B. So this is one of the form to represent it, and if somebody asks you about the second form of T matrix representation with respect to basis, this can also be written like coordinate vector of TV1 with respect to basis B, coordinate vector of TV2 with respect to basis B, or coordinate vector of TVN with respect to basis B, or simply you can represent it like this. We have A11, A12 and A1n, then we have A21, A22 and A2n. In a similar way we have AN1, AN2 and we have ANN. This is going to be the matrix representation for the linear transformation T with respect to the standard basis B. So now I hope the theoretical portion that I wanted to cover is clear to all of you. Even if it is not clear to few of you, just put your question on comment box and I'll try to reply to your question. Okay. So I hope the theory portion is much clear. Now we will go for a few questions so that it can develop a better understanding about the matrix representation. So let me go to the question number 1. Question number 1 that we have to do is our T from R2 to R2, and this T of x comma y is 2x minus 5y comma 3x plus y, and then we have basis of R2 as 2 1 and 3 2. Okay, I am starting from a very calculative question from the beginning itself, so that here also I'll give you a very short way to find out the matrix representation, and this will help you in exams as well. So suppose I have asked you to find out the matrix representation of this linear transformation T with respect to this ordered basis B. Okay, so according to the process that I told you just a few minutes back, you will consider these members as V1, V2, fine. And then what you are going to do is that you will find out TB1, that is your T of 2 comma 1, and according to the definition that is being given to you, you are going to apply it, and what it will be, this is going to be 4 minus 5, then here you will get 6 plus 1. What here you are getting? Minus 1 comma 7. So you are going to write it down in linear combination of the basis members. So this is going to be like this. Now what next you will do? You will find out TB2. This is going to be T of 3 comma 2. So this is going to be 6 minus 10 comma 3x plus y. This means 9 plus 2. Okay, so this is what we are getting. So this is minus 4 and 11. So again we will write it down in the linear combination of the basis members. So this is what we are getting. Okay, so if you are going to see, we have to solve two systems if you are considering them as a non-homogeneous system of linear equations, right? So the work is little more. So what we can do here is that you will write it down like this. I hope all of you know the process. I am just writing down the first one. This is minus 1 comma 7. So this is your A11, 2 times A11 comma A11, plus this is 3 times A12 comma 2 times A12, and I'll tell you the very short way also. This is just for your understanding. 2A11 plus 3A12, then here you got A11 plus 2A12. Okay, now you compare it. So what you are getting? 2A11 plus 3A12 as minus 1, then A11 plus 2A12 as your 7. So you can very easily solve it. You can just form the matrix, or you can just multiply it by 2 and then you can subtract it. The either way you want to solve, you can do it very easily. Okay, either by the matrix method. So what you can do here is that you just form the matrix and interchange the rows. Okay, this is your 7, then this is your 2 3, because this is the general method and it will help you out in other questions which are like R3 to R3. They will help you. So this you just apply the elementary row operation on row R2 as R2 minus 2 R1. So this will give you 0. Then this is 3 minus 4 minus 1. this is -1, -14, this is -15. Okay, so these are the values that we are getting. So very easily we can find it out that C2 is coming out to be 15, and from the first equation we have C1 plus 2, sorry, A11. Here we have A11 plus 2A12 equals to 7, and this was our A12. Okay, this was our A12. C2 is actually our A12. A12. So if we are going to keep it in A11, what we are getting is 7 minus 30. So what we got here is that minus 23. So TV1 we got like what? Minus 23 times what we are getting here is that 2 comma 1. We have 2 comma 1. Then we have plus 30 times 3 comma 2 plus 30, it's 15. Okay, it's 15 times we got 1 comma 2. Okay, this is what we are getting. So in a similar way we will find out TV2 in the linear combination. So let me just find it out that also. Okay, this is 3 comma 2. This is 3 comma 2. This is always a very difficult way to find it out, so I'll just give you one very easy way also to do this. In a similar way you will find it out for TV2. So I'll just simply solve it. This is our 2 comma 1, 3 comma 2, 2 1 3 2, and then we have minus 4 11. So you just interchange the two rows and you will get it. Yeah, so if you are going to interchange, what you are getting here is that this is 0, then this is you are getting as minus 1, because you are just multiplying the first row by 2 and subtracting it. So here you got minus 1, and this is minus 4 minus, you are getting 22. So you are getting what? You are getting your A22 as 26, and this is the first equation. So what you will get, A21 plus 2 times A22 as 11. So this is A21 is going to be 11 minus 2 times 26. So this is A21 is 11 minus 52. So what we are getting here is that 41. So we got T of V2 also, that is A21. A21 is minus 41 to 1, and then A22 is your 26 times 3 comma 2. And now you know how to find out the matrix representation. You just have to take the transpose of the coefficient matrix. So minus 23, 15, minus 41, 26 transpose, and here you got minus 23, 15, minus 41, 26. This was the complete process to find out the matrix representation of linear transformation. And by this time many of you might be feeling like, ma'am, this is a very lengthy process, and if we are facing this lengthy process in a vector space of dimension 2, then what we will do if the dimension comes out to be 3 and 4. But don't worry, I'll going to tell you a very easy way to solve this question, where we need not to solve this system twice to find out these scalars. So I'm just giving you a very short method. So we will follow this in the next question that we are going to do in this lecture also. So let's do that. So we were given a linear transformation T of x comma y as 2x minus 5y, 2x minus 5y, and then we got 3x plus y. Fine, 3x plus y, and then we have a basis which was given to us 2 1 3 2. Fine. Now you see how it is going to be very simple. You just need to understand one thing, because whatever we are going to find it out, either we are going to find out TV1 or we are going to find TV2, both are going to belong from where? From R2 itself. Why? Because this linear transformation is from V to V. So if we are writing down T of V is equals to W, then this W also belongs to where? Vector space V. So why we are solving this system twice? We can just do it in a simple go. let me tell you what we will do here is that we will just take a very a very general vector v x comma y from R2, okay, and we will represent this x comma y as linear combination of what? As linear combination of the basis members c1 times 2 comma 1, c2 times 3 comma 2, okay, and we will solve this system. This is going to be 2 1 3 2, and here we have xy. We will just interchange the two rows to make our calculations simple and easy, okay. So what we will do, 1 2y, then we have 2 3x. We applied the elementary row operations, okay, so this is going to be 0. Then here we got minus 1, and here we got x minus 2y, okay. So simply we got c2 as 2y minus x, and if we are going to write down the first equation, c1 plus 2c2 equal to y, we will get c1 is equal to y minus 2 times c2, that is 2y minus x. So what we are getting c1 as, this is y minus 4y plus 2x, so we are getting 2x minus 3y. Now see how simple it became. We just wrote down a general vector x comma y as c1 times, that is 2x minus 3y times 2 comma 1, and we wrote it down c2 times, that is 2y minus x times 3 comma 2. How simple it became. Now see, we just evaluated what? T of v1, that is our t of what? 2 comma 1, by using which definition? This definition, and earlier we did it. So t of 2 comma 1 was minus 1 comma 7. We will just use it from the previous one, that is minus 1 comma 7, okay. And then we got t of v2, which is our t of 3 comma 2, and what it was? It was minus 4 comma 11. So let me write down minus 4 comma 11. Now you see how simple it is. Compare it with this process. Which process? This is your x, this is your x, this is your y, this is your y. You just simply keep over here. So this is 2x minus 3y. What it is going to be? Minus 2 and then minus 21. See, this is 2 comma 1 plus 2y minus x, that is 14, and minus x is, this is going to be plus 1 and 3 comma 2. So what it became? It became minus 23 times 2 comma 1 plus 15 times 3 comma 2. In a similar way, this is minus 4 comma 11. What you are getting? This is minus 8, and then this is going to be minus 33, right? And this is 2 comma 1 plus 2y minus x, that is 22, and this is going to be plus 4, 3 comma 2. So what we are getting over here is that minus 41, 2 comma 1 and plus 26, 3 comma 2. See, here is a coordinate vector for TV1. Here we can get the coordinate vector, and now we can very easily find out the matrix, and it is going to be the transpose. So I am just writing it down like this, and see the answer that we are getting is same as we were getting previous, minus 23, minus 41, 15 26 and 15 26. See, so this process is quite simple. So instead of solving the system, the same system twice, we will just solve it once, and we can just substitute the value of x and y, and we can simply find out the matrix representation. Okay, so this was the question where I just mentioned one thing: instead of solving a system twice, solve it once. It will make your calculation easier and simpler while solving it in the exam. So we will do just one more question, and I will follow the same process of solving the system once, and you people also can just pause the video and solve this question and match the answer and see the solution that I am doing. So let me write down the second question that we have to do. The second question that we have is t from R2 to R2, and we have t of x comma y as x comma y, okay, and the basis that I have is 1 comma 2 and 2 comma 3. And in today's class, I'll give you a one short trick also to find out the matrix representation with one of the bases, and I'll tell you in the last. Okay, so this is the linear transformation, and all of you might be knowing what is the name. This is the identity linear transformation. We have learned as a special case in our previous videos. Okay, and we need to find it out. So as I have already told you, just take a general member x comma y, write it down as the linear combination. Okay, we will solve this system. This is 1 2, and I told you, all of you, while watching this video, pause the video, write down the question, solve it, then see the solution and match the answer and see you are getting it right or not. Okay, so this is 1 2 2 3 and xy. Apply the elementary row operations here. So here you will get 0, here you will get -1, then here you will get y minus 2x. So you got C2 as 2x minus y, then C1 plus 2 times C2 you are getting x. So C1 is x times, or x minus 2 times 2x minus y. Fine. So here what you are getting is that C1 equals to, this is your x minus 4x and plus 2y. So this is C1 is going to be minus 3x plus 2y. So you can here write it down, x comma y is equal to C1, that is minus 3x plus 2y times 1 comma 2. And in the starting of this lecture I told you, don't play anything about the position of these basis members, because if you do so, the elements inside the matrix will be going to be interchanged here and there and you will get a wrong answer. So make sure you are writing 1 comma 2 here only and 2 comma 3 in the second position, because this is the ordered basis. C2 is your 2x minus y times 2 comma 3. And now the question is very simple. How? You just need to substitute the values. Find out tv1. tv1 is your t of 1 comma 2. According to the mapping, every member is mapped to itself. This is going to be 1 comma 2 only. And then you keep it here. This is minus 3 plus 4, 1 comma 2, because your x is 1 and your y is 2. Okay, so you will simply get it like this. Minus 3 plus 4, 1 comma 2. Then here you are getting 2, and then here this is minus 2 times 2 comma 3. Then the next step is your t of v2. This is t of 2 comma 3, and you got it same like 2 comma 3. Now you keep the values here. So this is going to be minus 6 and this is plus 6 of your 1 comma 2, and then you got here like 4 minus 3, which is your 2 comma 3. So t of v1 what you are getting is 1 times 1 comma 2 plus 0 times 2 comma 3. Then t of v2 you are getting as 0 times 1 comma 2 plus 1 times 2 comma 3. So the matrix representation that you got of this identity matrix representation with respect to standard basis is nothing but an identity matrix. So this is the point that you can learn also, that for any vector space, if I define identity linear transformation, then corresponding to this identity linear transformation, the matrix that we are going to get is nothing but the identity matrix. If the vector space has dimension 2, then we will get a 2 cross 2 identity matrix for the corresponding identity linear transformation. If we have a vector space of dimension n, okay, I am giving you a general result. If we have t from v to v such that t of v is equal to v, which is our identity linear transformation, and then where dimension of the vector space v is n, what we are going to get here is that the identity matrix we will get for this matrix representation of t with respect to any basis. This is going to be like this, okay. And the story behind this is quite simple. If all of you can understand this, is that because if I want to write down any member, okay, you just have to think like this way. If I want to write down this member as a linear combination of these two members, what it is going to be? It is going to be 1 time itself plus 0 time other. So we don't have to evaluate this one, but since it is the beginning class, it is the first class on matrix representation, I am telling you this. Fine. So this was our question number 2, and now we will proceed to our question number 3, and let's see what we can do in this question number 3. Okay. So the question number 3 that we have is t from R2 to R2. We will do one more session on this, and we will practice as many questions as we can, and even I will come up with few PYQs on this matrix representation as well. And we have been given a basis 1 comma 2 and 1 comma 0, and क्लास एंड होते होते आई विल गिव यू अ वेरी शॉर्ट ट्रिक विच यू कैन अप्लाई, एंड इसका एप्लीकेशन बहुत अच्छा है इस टॉपिक का, मैट्रिक्स रिप्रेजेंटेशन का। तो जो आज ट्रिक हम पढ़ेंगे उसको हम कहीं पे भी अप्लाई कर सकते हैं टू गेट आर आंसर. So you just have to watch this lecture till end. Okay, so we need to find out the matrix representation of this linear transformation with respect to basis B. So again the similar process, we can write it down a general vector from R2 and we will write it down as a linear combination of this member. So see how simple it is. If you want to calculate it you can do it, otherwise this is very simple from here also. C1 plus C2, then we got 2C1 and plus 0, so this will not make any sense. So we got C1 as y by 2 as you can see from here, and C1 plus C2 is equal to x, so we got C2 also x minus y by 2. Otherwise what you can do is that you can solve it by system also. All the students who are solving, this is 1 2, then we got 1 0 and xy. You just apply the elementary row operations, or you can simply get it from here, but there is no need because very simple way we are getting the values of C1 and C2. Okay, so here what we can do is that we can just write down x comma y as C1 times, that is y by 2 times first member of the ordered basis, then C2 times, that is x minus y by 2 times the second member of the ordered basis. Okay, now what we will do, we will find out t of v1, which is what, t of 1 comma 2, and how we will use this, we will use this definition. Okay, t of x comma y is x plus y comma x, this is 1 plus 2 comma x, that is 1. So what we are getting is 3 comma 1. In a similar way we will find out t of v2. What is that? T of 1 comma 0, this is going where, x plus y, that is 1 plus 0 comma x, that is 1. So here what we are getting is 1 comma 1. So now it became very simple and we can find out the matrix representation. So I hope now all of you also can see that solving a system twice is not a good option. We will solve it once and we are very easily getting the matrix representation for any linear transformation. So t of v1 is our 3 comma 1. So you just substitute it here. So this is 1 by 2, 1 comma 2 plus x minus y by 2, it means 3 minus 1 by 2, 1 comma 0. What we got here is that 1 by 2 times 1 comma 2, this is your 5 by 2 times 1 comma 0. Fine. Then next what we are getting is t of v2, that is your t of what is being, it is 1 1. So what we will get, this is y by 2, that means 1 by 2 comma 1 by 2, and this is 1 minus 1 by 2, that is 1 by 2 times 1 comma 0. So if somebody asks you about the matrix representation, now it's very clear. We will take the coefficient of the transpose matrix. This is 1 by 2, this 5 by 2 will come here because we have to take transpose, then this is 1 by 2 and 1 by 2. Okay, so this is the matrix representation for this given linear transformation T with respect to this given basis B. Fine. So now I am going to tell you something which is very helpful for you, and I am doing the same question. T from R2 to R2, t of x comma y is your x plus y comma x. As you know that for any vector space there exist infinitely many bases. So now I am considering the standard ordered basis. Okay, here there was ordered basis which was not standard, and in this question I am considering a standard ordered basis, and what we have to do is that we have to find out the matrix representation. Today why I am solving or finding out the matrix representation of the same linear transformation with the two bases. Tomorrow I'll give you the answer for this question, why I am doing this, and you will also do the same thing from tomorrow because there is a very very logical thing about this because this will help you out in solving the questions in exam very quickly. So if we want to find out the matrix representation of any linear transformation with respect to standard basis, I will tell you the trick which you will apply in every question where you need to find out determinant, trace, or rank, eigenvalue, but just for the clarity purpose I am doing it here. We will write down any vector x comma y as a linear combination. The process that we are doing it so long, this is going to be x time 1 0. Without solving it we can get it. Okay, So here your t of 1 comma 0 is what? This is 1 plus 0 comma x, and this is your 0 comma 1 is your 0 plus 1, that is 1, and x this is. So you can very easily apply this formula which that we were using, what, this linear combination 1. So 1, this is going to be 1 times 1 0 plus this is going to be 1 times 0 1. Okay, this is going to be 1 times 1 0 plus this is going to be 0 times 0 1. Fine, this is what we are getting. What we have to do is that we will just take out the transpose of the matrix, and what we are getting, 1 1 1 0. Okay, and you don't have to do all these stuff. Why? I just told you the process, but here is a trick about it. What trick we are using here? And this is valid only in case of the standard ordered basis. I am telling you, don't apply it anywhere that oh ma'am told us and we are applying it. So before applying any trick you should know कि उससे पहले क्या क्या क्वेश्चन को फॉलो करना चाहिए. तो अगर आपके पास कोई भी स्टैंडर्ड बेसिस है तो आप डायरेक्ट मैट्रिक्स रिप्रेजेंटेशन लिख सकते हो किसी भी लीनियर ऑपरेटर का, यानी लीनियर ट्रांसफॉर्मेशन जो सेम वेक्टर स्पेस टू सेम वेक्टर स्पेस हो. कैसे? आप पहला वाला जो कंपोनेंट है वो उठाओ. ठीक है, पहले कंपोनेंट में जो x का कोफिशिएंट है वो लिख दो, जो y का कोफिशिएंट है वो लिख दो. पहली रो बन गई. तब आप दोबारा क्या करोगे, दूसरा जो कोफिशिएंट कंपोनेंट है वो उठाओ, उसमें जो x का कोफिशिएंट है वो लिख दो, जो y का कोफिशिएंट है वो लिख दो. दैट इज इट, आपकी मैट्रिक्स बन गई. ठीक है, एंड आप देखो यही हमने यहाँ पे भी फॉर्म करी थी. तो इन केस ऑफ स्टैंडर्ड लीनियर ट्रांसफॉर्मेशन आपको स्टैंडर्ड बेसिस आपको किसी भी लीनियर ट्रांसफॉर्मेशन की अगर मैट्रिक्स रिप्रेजेंटेशन लिखना है, आप डायरेक्ट इस ट्रिक का इस्तेमाल करके लिख सकते हो. अभी मैं आपको कुछ और क्वेश्चंस बताती हूँ जिसमें अभी मैं डायरेक्ट आपको लिख के बताती हूँ. सपोज मेरे पास t दिया होता R3 to R3, ठीक है, और मुझे t कोई भी लीनियर ट्रांसफॉर्मेशन ऐसे दिया होता. अभी हमने जैसे थोड़ी देर पहले लिखा था आइडेंटिटी का, जैसे ये आइडेंटिटी है. ठीक है, स्टैंडर्ड बेसिस के रिस्पेक्ट में हम लिख रहे हैं, तो स्टैंडर्ड बेसिस क्या होगी, इसकी यही होगी, विच एवरीबडी नोज बट स्टिल आई एम राइटिंग इट डाउन सो दैट नो बडी हैज़ एनी कन्फ्यूजन. तो अभी मैंने आपको क्या सिखाया, डायरेक्ट लिख सकते हो आप, है ना. पहला कंपोनेंट उठाओ, तो वहाँ पे x का कोफिशिएंट, y का कोफिशिएंट, क्योंकि इसको हम कैसे लिख सकते हैं, x प्लस 0y प्लस 0z. x का कोफिशिएंट 1, y का 0, z का 0. देन सेकेंड कंपोनेंट उठाओ आप, x का कोफिशिएंट, y का कोफिशिएंट, z का. थर्ड उठाओ, x का, y का, z का. देखो अभी तो सिखाया था थोड़ी देर पहले कि किसी भी आइडेंटिटी लीनियर ट्रांसफॉर्मेशन की किसी भी बेसिस के रिस्पेक्ट में जो मैट्रिक्स रिप्रेजेंटेशन बनाएंगे हम, वो आइडेंटिटी मैट्रिक्स बनेगा. सपोज एक कोई दूसरा ले लेते हैं हम, R3 to R3, and we are having x comma y comma z as x plus 2y, then we have minus x plus 2y minus 3z, then we have y minus 2z. अब स्टैंडर्ड बेसिस के ही रिस्पेक्ट में बनाना है आपको, किसी और बेसिस के रिस्पेक्ट में होगा तो आंसर कुछ और आएगा. डायरेक्ट बना सकते हैं. कैसे सिखाया है अभी मैंने, फर्स्ट रो फर्स्ट कंपोनेंट से लिखी जाएगी, सेकेंड रो सेकेंड कंपोनेंट से लिखी जाएगी, एंड आपके पास जो थर्ड रो है वो थर्ड कंपोनेंट से लिखी जाएगी. ठीक है, तो पहले हम फर्स्ट रो को देखते हैं. वहाँ पे x का कोफिशिएंट, क्योंकि ये x y z ऐसे ऑर्डर में चल रहा है तो आप ऐसे ही लिखोगे. सपोज यहाँ y होता तो पहला कंपोनेंट y का देखते, तो ये ऑर्डर बहुत मैटर करता है. x y z इस ऑर्डर में लिखा है तो x का कोफिशिएंट, देन y का कोफिशिएंट, देन z का कोफिशिएंट. z है नहीं, 0 हो गया. सेकेंड रो सेकेंड कंपोनेंट से लिखेंगे हम, तो x का कोफिशिएंट, y का कोफिशिएंट, z का कोफिशिएंट, एंड देन हम लोग जो लास्ट रो है वो लास्ट कंपोनेंट से लिखेंगे, तो x का कोफिशिएंट, देन y का कोफिशिएंट, z का. देखो आप मैट्रिक्स बन गई. और आप चाहो तो जो प्रोसेस मैंने आपको बताया था आप उससे निकाल भी सकते हो, सिमिलर मैट्रिक्स आएगी. सो आई होप दिस ट्रिक इज़ क्लियर टू ऑल ऑफ यू. और आज मैंने ये ट्रिक बताई क्यों है इसका जवाब भी आपको मिलेगा, लेकिन अगले लेक्चर में. ठीक है, सो उससे पहले जाते जाते सेशन को एंड करने से पहले एक क्वेश्चन दे देती हूँ मैं आप लोगों को, और देखती हूँ कि आप लोग कमेंट बॉक्स में कितने लोग हो जो उस क्वेश्चन का जो आंसर है वो सही बताते हो मुझे. ठीक है, तो देखते हैं और कितनी जल्दी बताते हो, क्योंकि कई लोग क्या होता है 2-3 दिन बाद आंसर कर रहे हैं, उसका कोई फ़ायदा नहीं है, क्योंकि कंपटीशन में आप पहले ही पीछे हो चुके हो, बहुत सारे लोग पहले आंसर कर चुके हैं. तो लेट मी जस्ट सी हाउ मेनी ऑफ यू कैन आंसर इट fastly in comment box and correctly. Most important thing is that correctly. So t of x, y, z we have been given as 2x plus 3y minus 4z, then we have y plus z, and we have 2y minus 9x, and the basis, the ordered basis that I am giving you is 1 2 3. We have 1 0 1. Okay, this is your 1 0 1, and then I am giving you 1 minus 1 0. तो आपके पास एक 3x3 की मैट्रिक्स बनेगी और वो आपको मुझे बतानी है कमेंट बॉक्स में, एंड देखते हैं कितने लोग इसका आंसर जो है वो सही से आंसर कर पाते हैं। तो आपको कल एक और लेक्चर मिलेगा। आज हमने बहुत बेसिक से क्वेश्चन किए हैं, लाइक R2 पे, R3 पे बेसिक कॉन्सेप्ट समझाने की मैंने कोशिश करी है। इम्पॉर्टेंट है ये टॉपिक। ऐसे आपको डायरेक्ट क्वेश्चन देखने को नहीं मिलेगा, लेकिन अगर आप देखो तो आइगन वैल्यूज़ पे क्वेश्चन आता है, रैंक पे क्वेश्चन आ रहा है, तो वो हम मैट्रिक्स की हेल्प से ही सॉल्व करते हैं। तो मैं इसको आपको एप्लीकेशन पार्ट जो है वो भी समझाऊंगी, बट इन द कमिंग लेक्चर्स। सो यू पीपल विल आंसर मी this question in comment box, and if you have any confusion regarding any question or topic or concept that I gave in this session, you can ask me in the comment box also. So let's see all of you in the next session. So that's it for it, but I will complete this particular topic in the coming sessions as well. Be regular to the videos, and आप इससे पहले कि ये वाले videos देखो, इनको देख के पुराने वाले भी complete कर लो, क्योंकि अभी जो सीरीज़ है वो रेगुलरली आने वाली है। आप लोगों में से बहुत सारे लोग परेशान भी थे, बट इन द लास्ट वीडियो आई हैव ऑलरेडी आंसर्ड इट बिकॉज आई वॉज नॉट फीलिंग वेल, सो थोड़ा सा डिसकॉन्टिन्यूटी आ गई थी, बट नाउ यू विल गेट रेगुलर लेक्चर्स. सो दैट्स इट फॉर दिस सेशन. थैंक यू सो मच.